Hi, my name is Vignesh, and this is the video of my science project. The first topic given to me is Hermite polynomial. Now, what are Hermite polynomials? The Hermite polynomials are basically a set of orthogonal polynomials. Now, a little bit of history. The Hermite polynomials was first defined by the French mathematician Laplace and developed further by Charles Hermite, another French mathematician, after whom it was subsequently named. A lot of work on Hermite polynomials was also done by the Russian mathematician Chebyshev. So, how do we define the Hermite polynomial? The first way to represent the Hermite polynomial Hn of z is through the contour representation. That is, by using the contour integral. So here Hn of z equal to n factorial by 2 pi I closed integral of e power minus t squared plus 2tz into t power minus n minus 1 dt, where the contour encloses the origin. Now for varying values of n from 0 to 10, we have the first few Hermite polynomials in this list. H0 of x to h10 of x. Now, this is the graph of Hn of x for values of n from 1 to 4. That is h1 of x, h2 of x, h3 of x, and h4 of x. As we can see, there are varying graphs representing each set of Hermite polynomials. Now, the values Hn of 0 are popularly called Hermite numbers. We already saw the contour representation of Hermite polynomials. Other than these, there are two standardized representations of Hermite polynomials. The first is the one more popularly used in physics, and it is given as follows. There is also an equivalent representation of Hermite polynomials, which are more generally used in probability. These are the two equivalent representations of Hermite polynomials. Other than these representations, there is also a modified version of the Hermite polynomial, which is Hen of x equal to 2 power minus n by 2 Hn of x by root 2. Now, let us look at some properties of Hermite polynomials. First, the Hermite polynomials are orthogonal in the range R, which we all know, with respect to the weighting function e power minus x squared. The entire equation is given below. Integral from minus infinity to plus infinity hm of x into hn of x into the weighting function e power minus x squared dx equal to delta mn 2 power n factorial root pi. The second property of Hermite polynomials is it satisfies a symmetry condition Hn of minus x equal to minus 1 power n Hn of x. The third property of Hermite polynomials is it obeys the recurrence relations. H of n plus 1 of x equal to 2x Hn of x minus 2n h of n minus 1 of x and h dash n of x equal to 2n h n minus 1 of x. These two recurrence relations are popularly followed by the Hermite polynomials. Fourth, the Hermite polynomials also obey the sum sigma k equal to 0 to n minus 1 power n minus k nck hn of k equal to 2 power n factorial. With these four main properties, we come to the end of Hermite polynomials. The next topic of the project is Laguerre polynomial. The Laguerre polynomials, named after the mathematician Edmond Laguerre, are solutions of the Laguerre's equation, which states that x y double dash plus 1 minus x into y dash plus ny equal to 0. These polynomials, usually denoted by L0, L1, L2, so on, are a polynomial sequence which can be represented by the Rodriguez formula, as shown below. The Laguerre polynomials are orthogonal polynomials with respect to an inner product. Next, another representation of the Laguerre polynomials, in addition to the Rodriguez representation, is given by the sum ln of x equal to summation k equal to 0 to n minus 1 power k by k factorial into nck into x power k, where nck is the binomial coefficient. Again, providing values of n here from 0 to 6 gives us the first 7 Laguerre polynomials, as shown below. Here is the graph for the Laguerre polynomials with values of n ranging from 1 to 5, from L1 of x to L5 of x. And we can see the varying graphs of each set of Laguerre polynomials. Next, moving on to the contour representation of the Laguerre polynomial. We first saw the representation of Laguerre polynomials using the Rodriguez formula. We also saw a representation using summation. This is the third representation of Laguerre polynomial, which is using the contour integral. Ln of z equal to 1 by 2 pi I closed integral e power minus zt by 1 minus t divided by 1 minus t into t power n plus 1 dt. Next, we have two properties of Laguerre polynomials. The first is the generating function of the polynomial, which is as shown below. And the second property is that the Laguerre polynomials are also used for Gaussian quadrature, that is, an approximation of the definite integral of a function. And the Laguerre polynomials can also be used to numerically compute the integrals of the common form integral from 0 to infinity f of x e power minus x dx. With this, we come to the end of Laguerre polynomials. Next, we come to the third topic of the science project, the moment of inertia matrix. The scalar moments of inertia appear as elements in a matrix when a system of particles is assembled into a rigid body that moves in 3D space. This inertia matrix appears in the calculation of the angular momentum, kinetic energy, and the resultant torque of rigid system of particles. Thus, the inertia matrix has a lot of applications. Now, let us explain how we obtain the inertia matrix. Let us consider a rigid body rotating with fixed angular velocity omega about an axis which passes through the origin. Let Ri be the position vector of the ith mass element whose mass is mi. Now, we expect this position vector Ri to precess about the axis of rotation, which is parallel to omega, with angular velocity omega. Now we can derive that dRi by dt equal to omega cross Ri. So here we have a cross product. We already know that the velocity Vi equal to dRi by dt. This velocity is of each mass element as the body rotates with fixed angular velocity omega about an axis, as we already specified, is passing through the origin. Here we can see the scenario. We have the omega axis, the Ri axis, and the origin. Now, the total angular momentum of the body L about the origin is written as follows. Here, as we can see, we know that L equal to m into v cross r. V can be replaced as dRi by dt. dRi by dt can further be replaced as omega cross Ri as specified above. Now, since this is a cross product, it can further be written in a matrix form. The matrix equation of this formula is given below. This matrix is called the moment of inertia matrix with all the values of I. As we know, it follows these given conditions too. To explain the terms better, the Ixx is called the moment of inertia about the x-axis. The Iyy is about the y-axis. Ixy is the xy product of inertia. Iyz is the yz product of inertia, etc. The matrix of I of ij values is known as the moment of inertia tensor. Now, the angular momentum vector L, as we know it, points in a different direction to the angular velocity omega. In other words, L is generally not parallel to omega. As concluding remarks, although the above results are obtained assuming a fixed angular velocity, they remain valid at each instant of time if the angular velocity varies. With this, we come to the end of the moment of inertia matrix. Next, we move on to the fourth and the final topic of the science project. The rocket dynamics using Lagrangian and Hamiltonian mechanics. For a rocket, the kinetic energy is k equal to half m q dot squared, where q dot is the velocity and m is the mass of the rocket at that instant. The potential energy U equal to mgq, where q is the position coordinate of the rocket. We know that the Lagrangian is defined as k minus u. Substituting k and u from the above equations, we get the Lagrangian for the rocket dynamics. We know the Lagrangian equation of motion. Dou by dou t of dou L by dou q dot minus dou L by dou q equal to 0. We have already learned this in the Science-1 class. Using this, we can get the resultant Lagrangian equation by substituting it as follows. It becomes d by dt of mq dot plus mg equal to 0. The resultant thus becomes mq double dot plus dou m by dou t q dot equal to minus mg. This is the resultant Lagrangian equation. Now let's move on to the Hamiltonian part. The Hamiltonian, as we know, is defined as k plus u. Again, substituting k and u from the above equations, we get the Hamiltonian. From the Hamiltonian equations of motion, we know that dou p by dou t equal to minus dou h by dou q. Here, p can be written as dou L by dou q dot, which is equal to mq dot. Now, substituting this, we get dou by dou t of mq dot equal to minus dou h by dou q, which is equal to minus mg. Thus, we obtain the Hamiltonian equation of motion for rocket dynamics. That is, mq double dot plus dou m by dou t q dot equal to minus mg. We can see that the Hamiltonian and the Lagrangian equations of motion match. Thus, our answer is verified. With this, we come to the end of all 4 topics. Thank you.